All right. So we're going to kick off here by considering quickly the example that we didn't get to last time. Figured this would be a good way of segueing into the idea of correlations. So remember last time we said there are two different versions of the governing equation which govern, this is important, which govern the mean temperature in flow through a pipe. Okay. And those two forms, we'll write them down in a second. Oh, may as well write them down now. R dTm dx equals P over m dot Cp times either Q double prime or P over m dot Cp times H Ts minus Tm. So you have two different versions of this you can use. In either case, it's going to be a differential equation, but one of these is good if you happen to know the heat flux rate. That was the example we did last time, something like a pipe wrapped in a resistance wire where you know how much power you're using in order that you're dumping into the flow. And one of them is good where you happen to know the surface temperature. Okay? And that's this case right here. The solution processes are going to look a little bit different for each of these two equations, but we should have the mathematical tools in hand to tackle either one. So remember, for this case, if we happen to know Q double prime, for example, if Q double prime is a constant, then we ended up with the result that this whole thing is a constant, therefore the derivative of equal to a constant indicates that we have a linear distribution of temperatures. So we ended up with this linear increase in Tm, or the mean temperature, with distance along the pipe, x. In this case, we have a Tm over here as well. Okay, so that's where we have to start considering, all right, what form is this governing equation going to take? So I want you to spend just another minute or two making some headway on this. And as we've done in similar problems in the past, namely, as we did the Finn equation, okay, we're going to use some substitution of variables. So we're going to define theta, which is the difference between the mean temperature somewhere in a pipe and the surface temperature, T sub s, and substitute that into the governing equation made up of this part and, well, let's go ahead and just get rid of this middle one and move that guy over. Okay, so we should be able to use that substitution to significantly simplify that, and we'll move on from there. So take 2 or 3 minutes, see how far you can get, and then we'll play catch up as a group. Yeah.
What's the diameter?
The diameter is, oh, you ready to leave that out? 0.1 meter. Okay, I'm gonna switch over to just for a moment. Okay, so substitution of that variable, right? By saying that, okay, by supposing that theta is equal to Tm minus Ts. Okay. Then we end up with theta, really we end up with, dTm minus over dx is equal to d theta dx and Ts minus Tm, right, is equal to negative theta, which should indicate to us, right, that our governing equation, if written in terms of theta instead of Tm and Ts, should look something like theta dx minus p over m dot cp times, plus h theta is equal to 0. Show of hands if you're here after a couple of minutes of fiddling around. Okay. I guess show of hands if that step makes sense. Okay. All right. So we did the same thing when we were dealing with the Finn equation, right? It's you can solve it in this form also, but it requires a couple of extra steps. And so by solving in terms of an alternate kind of dummy variable theta, we're just saving ourselves the trouble of having a non-homogeneous differential equation. Anyone know what kind of, so looking at this, having taken differential equations in the past, anyone know what kind of solution for theta this equation suggests? Why don't you consult with whoever the 2 or 3 people sitting closest to you and see if you can agree on a form of the solution, right? I don't need something exact, I just want the general type of function that theta should be. Any volunteers? Bingo. Heard exponential function, right? Because we've got a derivative plus that function itself multiplied by some constant has to equal 0. And the only type of function that satisfies that behavior is some exponentiated quantity. So this suggests, right, that theta is going to be equal to some constant times e raised to the negative ph over m dot cp x plus, well, there we go. We'll leave it that form because that's the most direct approach. The leap to get from this to this is something that, like, you can get to it more systematically as well. For example, if you were to move the dx over here, move the theta over here, you'll end up with 1 over theta d theta is equal to something in terms of dx, and you can separate it and integrate by both sides. You'll get a natural logarithm, okay? And if you raise both sides or if you exponentiate both sides, so in other words, e raised to both sides of the equation, then you'll end up with this again. So, but cultivate the ability, because this is one class, but many classes after this, right? Anything dealing with dynamics, structural dynamics in particular, the ability to look at these first and second order differential equations and recognize the form of the solution that you should be seeing, that's something you need to try to get comfortable doing. Anyway, so we're dealing with an exponential function with one unknown constant. That unknown constant comes from our one boundary condition, which in this case should pretty clearly come from the inlet temperature, right? If we wanted to, we could go ahead and now write this back in terms of Tm. So because theta is equal to Tm minus Ts, we have Tm minus Ts equal to Ce to the negative pH m dot Cp times x, which suggests that Tm is equal to Ce to the negative pH over m dot Cp x plus Ts, right? So at the inlet condition, where x equals 0, we have that Tm is equal to T in, or 25 degrees Celsius. So at that condition, right, e raised to the 0 gives us 1, and so we should end up with 25 degrees Celsius is equal to C plus Ts, when Ts is 100 degrees Celsius, which suggests that our constant there is negative 75 degrees Celsius. All right, we could do this in Kelvin as well. Doesn't really matter. We're going to get the same solution. So in the end, right, our equation for Tm, as a function of x, is going to be 100 degrees Celsius minus 75 degrees Celsius e to the negative pH m dot Cp x. Okay. P is going to be the perimeter of our pipe, right? So we're given the diameter. Thanks for noticing that wasn't provided. Pi times the diameter, we're going for P. H, we are told to go ahead and assume 10 watts per meter squared Kelvin. M dot is given as 0.01 kilograms per second. Cp is given as 1 kilojoule per kilogram Kelvin for fluid. And so plugging this all in allows us to evaluate T sub m at any point along the pipe. So what we're seeking, right, is the temperature at the outlet of the pipe, 30 meters downstream from where it comes in. Simple enough to evaluate. Tm out is equal to Tm at 30 meters, should be 100 degrees Celsius minus 75 degrees Celsius, e to the pi times 0.1 meter. Go ahead. 0.1 meter times 10 watts per meter squared Kelvin. .01 kilogram per second for m dot, 1,000 joules per kilogram Kelvin for Cp times 30 meters. And plugging this into our calculators, we should end up with something that looks like approximately 99.99 degrees Celsius. So it has reached almost complete thermal equilibrium with the pipe. Give everyone a minute to mull that over. Any questions on what we did there? Yeah. Oh yeah, this is supposed to be a negative number. Sorry, just dropped that negative. Okay. So what this suggests, right, is that for a constant surface temperature, we end up with this, we end up with a fairly large difference where x is smallest is where, where this quantity here is going to be largest. So what this suggests is that when we have, say we have x, and over here we have the temperature, that when we have a constant surface temperature, right? So let this be the surface temperature of our pipe. It suggests that our mean temperature is going to behave sort of like this, right? It's going to asymptotically approach the temperature of the surface. All right. So with this problem and with the one we did at the end of last lecture, where we had the constant Q double prime, in both of those, there was a theme that kind of made things a lot easier, and that was we were given H. So in internal convection, as in external convection, right? This is great. We can do surface balances, or energy balances. We can compute changes in temperatures, but our convection specific question here really should be how do we find H? So the same thing that we were trying to determine for external flows. And the solution to this question, or the answer to this, is going to be largely the same. We're going to use correlations that have been predetermined based on simulation, experiments, and in some very simple cases, people actually crunching through the exact solutions from the governing equations. So for example, if you assume laminar flow, you assume fully developed flow, it is possible, we're not going to do it, but it is possible to determine the solution exactly. We did something similar with like the flow between two pipes, or between two plates. Remember, we set up the governing equation, the Navier-Stokes equations and the energy equation, and we solved both of those and figured out a value of H. That was on the last homework. You can do the same thing for laminar flow through a circular pipe. And what you would end up with is, as an example, the Nusselt number based on diameter. So this is H times D over conductivity of the fluid is equal to 4.36 for uniform Q double prime and 3.66 for uniform pipe surface temperature. That's pretty nice. We just got single numbers to deal with. But this is for only laminar fully developed flow. And by fully developed, I mean thermal and hydrodynamic. The rest of the correlations, we're not going to go through all of them. But you should, from the previous chapter and from working on the project, you should begin to get comfortable with using these correlations and how to implement the ones that are in the back of the respective chapters. There's a lot of things that can complicate this, right? 4.36, 3.66, these are kind of uncommon flows. Perfectly fully developed, totally laminar, through a circular pipe. More often we're going to have complications, like what if the flow isn't fully developed, right? What if it's turbulent? And in those cases, we're going to turn to table 8.4. In the back of this chapter, which, similar to 7.7 in the last chapter, lists pretty much everything we're going to need to know for the purposes of this course. So we've got F, right, friction factors, if we're trying to deal with pressure drop, which is not going to be a focus of this class. More important, we've got Nusselt numbers, both local Nusselt numbers and averaged Nusselt numbers based on diameter for laminar fully developed flows, for laminar flows where there's a thermal entrance length, it's not fully developed, turbulent fully developed, for a couple of different cases. We've got the turbulent fully developed, 3 different versions of correlations, which are all valid. Sorry, these are friction factor. These 3 equations right here are all valid choices for computing the Nusselt number in fully developed turbulent flow. Some of them apply for different ranges. So the idea here is take your problem, compute, Prandtl number, figure out your Reynolds number, and look at the right-hand column over here and find the case that most closely matches what you're looking at. And bingo, you've got the correlation to use for your Nusselt number or your friction factor, if that's what's important. To illustrate, we'll go ahead and do a similar example to the one that we just covered, but we're going to go ahead and assume one that's not quite so classical. We're going to find H ourselves. I want to remind you again. Reminder that Nusselt number based on diameter is equal to H, D, or Kf. This is our local Nusselt number. And we say D is equal to H prime over Kf, which is our average. Okay, we'll talk in just a second about what we really mean by the average Nusselt number in this case, and why that's a little bit different for a internal flow through a pipe than it is for external flow over, say, a flat plate. Okay, so this is going to look a lot like the thing we just did, as I said. Let's say we have a pipe with a diameter of 50 millimeters, a length of 25 meters, and a constant surface temperature of 150 degrees Celsius. Okay. Into this pipe, we have flowing engine oil. At an inlet mean temperature of 20 degrees Celsius and a mass flow rate of 0.5 kilograms per second. So based on this information right here, we want to find, once again, the outlet mean temperature and the total Q, the total power that's being expended in heating up the oil as it flows through this tube. All right. Give you guys a second to copy down the prompt. Okay. So the setup of the problem should look just like the one we did a moment ago. Okay, so we can use the first few steps from our solution a few minutes ago to make significant progress on this one, namely, what version of the governing equation are we going to use? Well, dtm dx is equal to p times h over m dot cp ts minus tm. Right? Making our same substitution of theta equal to tm minus ts. End up with d theta dx plus ph over m dot cp theta is equal to 0, which suggests that theta is equal to c e to the, instead of writing c, I'm going to go ahead and use this notation. Hope that's okay. It makes it easier for me to write it without cramping everything together. Okay, once again, we can even go so far as to use our boundary condition at the pipe inlet to find C. So at x equals 0, well, let's solve it in terms of t first. Let's say tm then is equal to c exponent negative p times h over m dot cp x plus ts so apply our boundary condition at the pipe inlet, x equals 0, tm in is equal to 20 degrees C, which is equal to C plus ts. Which suggests that C is equal to negative 130 degrees Celsius. And we can write our particular solution now as Tm equals Ts minus 130 degrees Celsius exponent negative P H X over m dot Cp. Great. It's pretty straightforward, but we're kind of stuck now. Okay? Because, unlike before, we're not given H. We don't know Cp implicitly. Alright, so we're going to have to pull these data out of, as usual, the back of the book. So the question we need to ask ourselves is, we're talking about engine oil. If you look at the back of the book, engine oil, the properties, in particular the convective heat transfer coefficient, the conductivity K, which is going to be important for redimensionalizing our Nusselt number, and Cp here. These are all highly dependent on temperature. So what temperature do we use to look up those properties from the back of the book? The way we would do it, right? Let's say we're all seeing omniscient beings, would be to define a reference temperature that is T in plus T out over 2, right? The average of the average temperatures at the inlet and outlet, halfway through that process of heating up. Seems like a pretty reasonable approach, right? The issue is we don't know T out yet. Okay, that's what we're looking for. So our approach to the problem hinges on the solution to the problem. And there's no way of getting around that. What we're going to do is go ahead and first make an initial guess at what T out is. We're going to use that to look up the properties from the back of the book, and we're going to see what kind of T out we calculate with the solution to the problem. If those two things don't match, we're going to need to update our guess and iterate on the solution process until the T out that we guess and that we use to look at the fluid properties matches the T out that comes out the other end of the problem. So let's go ahead and assume make an initial guess that T out is equal to, say, 34 degrees Celsius. In this case, then, Tref will be equal to 20 degrees Celsius plus 34 degrees Celsius over 2, which is 27 degrees Celsius, or 300 Kelvin. And if you go to table A5 in the book, you can find, there we go, engine oil at 300 Kelvin. We've got a density of 884 kilograms per meter cubed, a specific heat capacity at constant pressure, CP of 1909 joules per kilogram Kelvin, a kinematic viscosity nu of 5.5 times 10 to the negative fourth meters squared per second, a conductivity K of 0.145 watts per meter Kelvin, and finally a Prandtl number of 6,400. So, be clear, these numbers are only valid as long as our guess, right, at 34 degrees Celsius is considered to be pretty close to what we get at the end of this problem. If they don't match, these numbers aren't reflective of what's actually going on in the problem, and our entire analysis is predicated on this false assumption. This values must okay. So, now that we've got some fluid properties, the next thing we want to do is find H. Okay. To do that, we need to know a few things. So, looking at the back of the book, we need to know. We'll pull up that table 8.4 in a second here. Want to know A, is it laminar or turbulent? B, is it fully developed or is it still developing? And are there any other properties that we're going to have to, any other dimensionless numbers we're going to have to calculate will be informed by the answers to those questions. So first thing, flow regime. What's the Reynolds number for this flow? Well, we define the Reynolds number, right, as the mean velocity times the diameter over viscosity. The mean velocity, of course, is equal to m dot over rho times the cross-sectional area of the pipe. Should be 0.5 kilograms per second divided by 884 kilograms per meter cubed. times pi 0.025. Sorry, that's 0.025 meters squared. So this should be 0.288 meters per second. Okay, so now with that number substituted in here, should be able to find a Reynolds number based on diameter of 0.288 meters per second times 0.05 meters for the diameter over 5.5 times 10 to the negative fourth meters squared per second, which works out to around 26.2. Okay? Meaning our flow regime is laminar. Very much so. Right? That's way less than the 2300 at which we begin to suspect that our flow might not be laminar anymore. Okay, so great. So that constrains us to looking at laminar flows in table 8.4. Give you guys a minute to finish copying that down. We're going to oops. Okay. Next question, is the flow fully developed? We'll consider first whether it's hydrodynamically fully developed. So remember the for the hydrodynamic hydrodynamically fully developed flow, we had that relationship that said that x FDH is equal to, well, approximately equal to 0.05 times the Reynolds number times the diameter, which works out to about 0.0655 meters. Compared to the overall length of the pipe, this is really small. Okay. So the idea here is, I mean, this is around what? Approximately 0.2% or something of the length of the pipe. So we're talking about just a minuscule quantity of the pipe in the hydrodynamic entrance length. So we can say that the flow is hydrodynamically over almost the entire length. Okay. What about thermally? I'll let you guys take a whack at this for just a second. Remember, we've got a different expression for the entrance length, the thermal entrance length in a pipe that uses the Prandtl number as well. All right. Anybody have a guess at the thermal entrance length of this pipe?
8,384.
8,384. Okay. It is going to be a really big number, but not quite that big. What expression did you use for?
0.05 times Reynolds number times Prandtl number.
Okay. That's right. But don't forget the diameter, because that 0.05 times Reynolds number times Prandtl number is actually for the ratio of the entrance length to the diameter. So what we really want is the 0.05 times Reynolds number based on diameter times Prandtl number times diameter. So it's just going to be that 8,000 some times the diameter of the pipe times 0.05. And what you should end up with here is something around 419.2 meters. Okay. Which in this case is much larger than the 25-meter length of the pipe. Which means the flow is not thermally fully developed. So we're dealing with an entry flow, a thermal entry flow. Okay. Now if we zip over to table 8.4, back of chapter 8, that means we're looking at, if we look at this first two Nusselt numbers, these are both a fully developed flow. 857, laminar, bingo, thermal entry. Okay, that's what we've got. It's hydrodynamically fully developed, but not thermally fully developed. This is a very common case. In fact, it'll occur a lot of the time when the Prandtl number is large. It's very uncommon that you'll have a thermally fully developed flow that is not yet hydrodynamically fully developed. So they haven't even bothered giving us a correlation for that case. We have a case for thermal entry or combined entry, which is when it's neither hydrodynamically or thermally fully developed. Anyway, so the one we want here is 857, which has this new variable in there, right? GZ. So in order to use this equation, right, that the mean Nusselt number based on diameter is equal to 3.66 plus 0.0668 GZ based on diameter 1 plus 0.404 GZ based on diameter raised to the 2/3 power. We have to calculate this thing called the Gratz number, which is defined as d over x times the Reynolds number based on diameter times the Prandtl number. So for this particular flow, okay, this x here should be, right, we're dealing with the mean Nusselt number, which means it's the average between the beginning of the pipe and some position x. And so where that x comes in is through the Gratz number. So if we want the mean Nusselt number over the entire length of the pipe, we need to plug in L for x, right? The total length of the pipe is at 25 meters. So GZ based on diameter is going to be equal to 0.05 meters over 25 meters times 26.2 times 6,400, which should give us a value of 335.4. Okay. Taking that value and substituting it into our correlation for the mean Nusselt number, now we should end up with, I'm not going to write out all of the values here explicitly, but if we plug that into the Nusselt number, we should end up with a value of 11.3 to the mean Nusselt number. So we said we recognize it's not fully developed. We said that means it's an entry flow. For entry flows, we have a special correlation there. We calculated the Gretz number based on how far down the pipe we want to consider, right? In this case, the entire length. Calculate the Gretz number, plug it into that correlation, and we get the Nusselt number. And finally, and this is where we'll leave things off, we'll finish it off on Monday. This means that H bar can be computed as Nusselt number based on diameter times K over D, which works out to 11.3 times K, 0.145 watts per meter Kelvin, and diameter is 0.05 meters. So this should give us a value of 32.77 watts per meter squared Kelvin. Okay, so at this point we have our H. Okay, we have our H. We have at least initial guesses at CP. And so we should be able to plug this as well as our initial guesses at the fluid properties into this expression right here, okay, and calculate what the outlet temperature is using the same process we did for the first example. Now, as I said, then what you do is you'd look at T out. Does it match my initial guess? If yes, you're done. If no, you have to update that guess and go through and calculate rho, CP, K, viscosity, Reynolds number, Gretz number, etc. One more again, and then check again and iterate until those two things match. So we'll briefly review this on Monday. Until then, have a good weekend.